All right, so these first lessons, I think there's 4 of them, are all called circular motion and Newton's laws. They're just broken into parts. What we're going to be doing today is relating what we learned yesterday to acceleration and force. And I'm going to start off by reviewing some things from yesterday, and I'm not going to spend a whole lot of time on this. But when you have an object moving in a circular path, if it's moving at a constant speed, we call that type of motion uniform circular motion. And the velocity at any point in time is tangent to the circular path. So if I just jump ahead, I just want to look at that diagram that's on the same page that we're talking about. When I take a look at this tennis ball on a string, if it's rotating clockwise, then at this instant in time, the velocity is indicated by this direction. And if the tennis ball were over here, the velocity would be in this direction. And if the tennis ball were here, the velocity would be in that direction. And these directions are what we call tangent to the path. What a tangent really is it's a line that's perpendicular to the radius. So this velocity that I've written in yellow is perpendicular to the string. This velocity that I've written in yellow is perpendicular to the string. So another way of saying that the velocity vector is tangent to the circular path is to say that it's at right angles to the radius. The other thing that we learned yesterday, well, there were a lot of things, but we learned that the velocity is continually changing because the velocity includes direction. So if the direction changes, the velocity must change. But you should know from kinematics, a changing velocity means an acceleration. So even though it's moving at a constant speed, even though the object is moving at a constant speed, it's still accelerating. The word accelerating in this context doesn't mean speeding up. It means changing velocity. We'll get to today what the significance of that acceleration is. We also talked about the fact that the only thing that makes sense is the acceleration is towards the center. And I'm going to go back to my diagram of the tennis ball here. The acceleration has to be towards the center because I'm looking at that blue vector. If that blue vector were not towards the center, if that blue vector instead were even a little bit in this direction, there is a component to that blue vector that is acting in the same direction as the velocity, which would mean the velocity would increase in value. So there's no way that that blue vector can be in that direction because it would speed the object up. And if the blue vector were in this direction, if the blue vector were in this direction, then there would be a component to the acceleration that would be acting backwards, and the velocity vector would decrease. So the only thing that makes sense is that the acceleration is towards the center. Now, what about the force? Well, if the acceleration is towards the center, the net force is towards the center. And I'm not trying to be facetious here. I'm being absolutely serious. This is Newton's second law of motion. The net force is in the same direction as the acceleration. It's the law. Both the acceleration and the net force are called centripetal. That means center seeking, so that's a reminder to you that they are towards the center. And these aren't just details that you have to memorize because I might ask them of you. These are details you need to know to apply physics. The thing that I can't stress enough throughout this part of this unit is that the centripetal force is the net force. If the object is a tennis ball on a string and I'm twirling it around, then I am applying a net force towards the center, so the centripetal force is an applied force by me. If we're talking about the moon moving around the Earth, so I can easily change this question and say, forget about a tennis ball. Let's say that this is the Earth and this is the moon, there's a force of gravity pulling the moon towards the Earth. So the centripetal force is the force of gravity. A centripetal force is not some special type of force. It's just whatever the applied force pulling the object in happens to be. Also recall from yesterday, and I've already talked about this today when we did our review before we went over the assigned problems, that the period of revolution is the time for one revolution. It's measured in seconds. The frequency is how many complete revolutions happen in a second. They are reciprocals of each other. The period is in seconds. The frequency is in hertz. And we've developed this formula that's on your formula sheet that really is just taking the circumference of an orbit divided by t equals v sub c. And I have a mistake here in this formula. It's not a glaring mistake, but I suppose I should correct it. And I'm not sure if it's in your handout, but this should be capital T on the bottom. So if it's lowercase t, that is important because lowercase t is just time. Capital T is a very specific time. It's the time for one complete revolution. Okay, so it turns out, and this is the thing, I really hate doing this to you, but there is sometimes a situation in high school science where I can't justify the formula. And this formula for the magnitude of the centripetal acceleration is a very weird formula. It says if you take the speed that the object is moving in a circular path and you square that speed and divide by the radius, you're going to get the centripetal acceleration in meters per second squared. And in order for us to understand where that formula comes from, we would have to use calculus. Now, that's not entirely true. If you look in your textbook does a geometric proof of that formula, but it really is beyond the scope of this course. It's very, very complicated. And I think if I went through it, 2 or 3 of you might get it. I'm not putting down the rest of the class, but it's very, very conceptual, like really conceptual. 2 or 3 or 8 or 10 might get it, but the rest who don't would be very confused, and I would cause more damage than good. So we have this formula for centripetal acceleration magnitude. Notice in the formula there's no direction. Why is there no direction? Because the direction of the acceleration is always changing. It's always towards the center. So when an object is at the bottom of its orbit, the centripetal acceleration will be up towards the center. When the object is to the right of the center, the centripetal acceleration will be towards the left, towards the center. So this is changing all the time. First question here, use the formula above, and I'm going to rewrite it. And just like my speed formula, I tend not to put vector symbols here. So we want a new formula for centripetal acceleration in terms of r and t. Well, we know that v is 2 pi r over the period. So what I am going to do is I am going to take this, which is speed, and put it right here because speed is 2 pi r over t. So I'm going to build a new formula through substitution. And the new formula will be the centripetal acceleration has a magnitude of 2 pi r over t squared divided by r. That's v squared over r. What does that give us? It gives you centripetal acceleration is, well, when you have something, I'm just going to turn this into a mini math lesson. When you have something like 2 times pi times r over t squared, that means it's 2 squared times pi squared times r squared over t squared. You are allowed to distribute that square everywhere. So we end up with 4 pi squared r squared over t squared, and the whole thing is divided by r. And I want you to note that I've drawn a very long line to represent the entire fraction. Because what this is, I'm getting into a math lesson here, is it's that divided by that. The reason why I need to do that is I think it's important that you understand that 100 divided by 20 over 5 is not the same thing as 100 divided by 20 over 5. They're different. The left side of this is 100 divided by 4, because 20 divided by 5 is 4. The right side is 5 divided by 5. They're different things. I end up with the number 25 here. I end up with the number 1 here. So now how do we handle this? Well, if it were a Math 30 class, and it isn't, we have a different way of simplifying this. What we're going to do is write this r as r over 1. And remember that when you take one fraction, like 4 pi squared r squared over t squared, and divide by a second fraction, the rule in mathematics is that you multiply by the reciprocal instead. So instead of dividing by r over 1, we multiply by 1 over r. And now I get the centripetal acceleration equals 4 pi squared r squared over t r, because when you multiply fractions, you multiply across the top, you multiply across the bottom. Why am I showing you the derivation of this formula? And we're not done yet. I think it's valuable for you to understand why I'm doing this. There was a time in the past where I wouldn't do this, because it's not physics. But I want you to understand where this formula comes from that we're going to develop, so you're not confused by it. And I also think it's a good exercise to get your brain going. I truly, sincerely believe that. What happens here is you have r squared on the top and r to the 1 on the bottom. So if I had r squared, which is r times r, over r to the 1, one of these r's cancel. So I get a new formula for centripetal acceleration. I guess I'll put the absolute value signs in, of 4 pi squared r over t squared. And that's the new formula. This grouping of r's, this r squared on the top over r on the bottom, gives you r on the top. Did I forget to square the t? Thank you very much. I forgot to write, thank you Liam, that it is over t squared definitely. We had squared the t over here. So the reason why it wasn't squared in the other is that I just forgot to write it down. Would we have to show this on an assignment, Ben? Absolutely not. I could have just given you the formula. What I could have said is that, well, let's look at the formula sheet now. Just give me a second. I could have said that centripetal acceleration, Ben, equals this, and that's beyond the scope of the course to develop the formula, and that's true. I could have lied to you and said the centripetal acceleration can also be found using this, and the math to get that is beyond the scope of the course, but that would be a lie. You are not expected to know to derive that formula, but I think it's important that you understand all this second formula is what we get when we use this formula combined with this formula. Okay. All right. Explain what you would do to the centripetal acceleration of a mass to determine the centripetal force. And this thing that I've talked about already once today and a couple of times yesterday is really crucial. The net force is the centripetal force. A centripetal force is a net force. So if net force is mass times acceleration, then the centripetal force, which is the net force, is equal to the mass times the centripetal acceleration. So what do you do to the centripetal acceleration to get the centripetal force? Or what do you do to the centripetal force, what do you do to the centripetal acceleration to get the net force? You multiply by the mass. It's Newton's second law. Okay? So now what we have are all of these formulas. I want to run through them one at a time, and then we're going to do some calculations with this stuff today. So the first formula relates period and frequency. That should be no problem. The second formula is how you calculate centripetal speed using the radius and t. And again, this should be capital T, the period. The third formula is the definition of centripetal acceleration. And you can calculate centripetal acceleration using v squared over r or 4 pi squared r over t squared. And then the last things on the bottom of this screen you're looking at, these are not on your formula sheet. This is just saying if you want to find the centripetal force or the net force, because they're the same thing, you take the mass times the acceleration, but the acceleration is v squared over r, or the acceleration is 4 pi squared r over t squared. So if you look at your formula sheet now, if you go to your formula sheet, I've clipped part of it up here. We have finally gotten to the stage, everybody, where you know about every formula under kinematics. Every single formula here is now known to you. We have the new formulas of centripetal speed, and then I don't know why, I wish they had two separate formulas here. They've got the two formulas packed together for centripetal acceleration. Right next door to it under waves, we have this formula, and that's the only formula that you know so far in that section. All right, now let's get to the part of the lesson that I think most people are more comfortable with, and that is calculations. So let's read this question together. We have a 50 gram mass in a centrifuge. Now what a centrifuge is something that spins very, very fast. So typically you have a test tube and you have different materials in the test tube. Maybe there's a sediment or a precipitate in chemistry, but in the test tube, there's this solution, and inside of it is this precipitate. And if you've taken has anybody taken Chem 20 here by a yes in the chat room? So if you've taken Chem 20, you learn that when you mix chemical solutions together, sometimes you get what's called a precipitate, which is little solid particles being formed due to chemical reaction. And if you want to separate the liquid or the solution from that precipitate, then you take this and you spin it around. So it goes in, it's kind of laying at an angle, but I don't want to draw it three-dimensionally. It goes in a device that you would put other test tubes in, and this thing spins very fast. If you've ever had a bottle of ketchup at home and you don't have much ketchup left, but you want to get the ketchup to the end, so here is a ketchup bottle. Let's say it's a glass ketchup bottle, and there's, ketchup stuck to the end here. What you do is you turn it upside down and you hold it so the lid is towards the bottom, and then you could hit it, or this works better, try it, swing it around. Imagine holding it, I wish I could show this to you, but imagine holding it by this part, but so that it's pointing down. So your hand is around there, and then swing your arm very, very fast back and forth. What you will discover is all of this catch-up ends at the bottom. So a centrifuge spins this test tube very fast. That's what a centrifuge is. It's rotating at 300 RPM, which is 300 revolutions per minute. We are going to need to know the frequency in hertz. This is a frequency. I would like everybody to figure out what the frequency in hertz is. It's 300 revolutions per minute, and hertz is revolutions per second, and there's 60 seconds in a minute. When you get the number of hertz, which is revs per second, you can go ahead and type it into chat. It is indeed 5 because you're going to take 300 divided by 60. Now, why do we need that? Well, look at what the question asks. The question asks for the centripetal acceleration, which is v squared over r, and I'm going to show you how I do this question, okay? This is how I do it. Look at the screen. I've got acceleration equals v squared over r, so my brain says I need v. How do I find v? 2 pi r over t. So because I know the frequency, I need to determine the period. And listen to this before you do any calculations. I'm going to find the period so that I know what number to put here so that I could calculate the speed, so that I can put the speed here so I could calculate the acceleration. And once you get all of this organized in your head, it is not a difficult problem. Like anything else, you get better with more practice. We calculate the reciprocal of the frequency, and that's going to give us 1 divided by 5 hertz, which gives us 0.2 seconds. I can now calculate the speed, 2 times pi times 0.065 meters divided by 0.2 seconds. I'm just using 2 pi r over t. Of course, we have to use standard units, so that 6.5 centimeters has to be divided by 100. Now I divide by the t, which is 0.2. Does anybody else get 2.04? That cannot be, it is? It is? Okay, so 2.042 meters per second. And now I can go over here and take the speed, which is 2.042 meters per second, squared divided by the radius, which is 0.065 meters. And this is going to give me the centripetal acceleration. So I square that divided by the radius, 64 meters per second squared. We are also asked, I believe, to find the centripetal force. So this is one of the answers to the question. Before I find the force, I need to tell you something that, so somebody got 1.6? So I just want to check with Andrea, and Andrea, you're talking about V. Did I enter it into my calculator incorrectly? 2 pi times r divided by 0.2 Whoever's speaking, I can barely hear you. Is it, okay, let's back up. Is it 0.2? Did I calculate that correctly or incorrectly? Is 1 divided by 5.2? Okay, so just check that calculation. 1 divided by 5 is 0.2. It might make that big of a difference, but it is 0.2. So if you thought it was 0.25, and I'm just kind of wondering why you get 0.25, but that's okay. If you thought it was 0.25, let's see. Two pi times 0.065 divided by 0.25. What did I do there? Oh. Yeah, so somehow, and it's a coincidence, it's a really interesting coincidence because both of you are Andreas. I don't know how that worked. I thought it was a 5. So JV, what are you saying there? Let's figure out what...
I thought it was a 5.
Oh, thank you, Andrea and JV. Ah, the elusive letter S that sometimes looks like a 5. Ah, okay. So, are we okay now, Andrea? Okay, good. Sorry about that. So 64 meters per second squared. Now I have to explain something to you, and I don't know where you're going to land on this. This is how I think. I find V first so I can find A. You could have, to find A, you could have used the other formula. And just to demonstrate that to you, I don't know why. I think it's because in Physics 30 we don't rely on that second formula. Let me show you that if I just took 4 times pi squared times the radius divided by t, which is 0.2, squared, I still get 64 meters per second squared. So we could have done that. Now the other thing you're asked to do is find the centripetal force. And since the centripetal force is the net force, we can just take the mass times the acceleration. So if I take, I think it was 50 grams, which is 0.05 kilograms, that is a 0. And multiply by the 64 meters per second squared, I'm going to get the centripetal force acting on it. And when you take those two numbers and multiply them, you get 3.2 newtons. So I know that I've written net force here, but net force is the same as centripetal force. So I'm going to pause there. Any questions with the calculations? Now there's one other thing we're asked to do here, and that's to compare what's going on to gravity, to the acceleration due to gravity. So if you take a look at the centripetal acceleration, the centripetal acceleration divided by the acceleration due to gravity is going to be 64 meters per second squared divided by 9.81 meters per second squared, which is very close to 6.4. Well, let's figure it out. I say it's very close to 6.4 because 9.81's, as my grandpa would say, pert near 10. So you get 6.54 apparently. What does this mean? It means that the acceleration of the mass, and we're going to use this notation a lot, the acceleration of the centripetal effect is 6.54 Gs. It's 6.54 times greater than the gravitational field strength of the Earth. So if you were, this is going to be weird for you to think about, but if you were in a giant centrifuge and you were standing somewhere inside and it were spinning, and the centripetal acceleration was 64 meters per second squared, then you would be able to walk around on the inside of that, just like the socks in a dryer when it's spinning or a washer when it's spinning stick to the outside. You would be able to walk around, but you would feel 6.5 times the force of gravity. So I don't really know how successful you would be in walking around. It would be like you were carrying 5 identical people on your shoulders. All right, let's move on. Let's take a look at the next question. Number 2, a Blu-ray disc has a diameter. Okay, I'm not going to make that same mistake twice. The radius is 6 centimeters because that's a diameter. And a rotational period, which is capital T, is 0.1 seconds. What's the centripetal acceleration at the outer edge? So what I would like you to do is calculate the centripetal acceleration. You can calculate V first and then use A equals V squared over R. So this is option 1. It's what I prefer to do, or you can dive right in head first into this more complicated formula, which is option 2. And, you know, in this particular question, since you're given all this information, I might choose option 2 here. But I'll give you a minute. You have to use standard units, and we will compare our answers. And just to let you know where my head is at this morning, I think what we're going to do is finish this lesson. I could pick up the speed a little bit so we could squeeze in the second lesson today, but looking at my calendar, I think we've got lots of time still. So I think we'll do this one lesson today, even though I told you we were going to do 2. All right. Please type an answer into Google Chat. Or please type yes in Google Chat if you have an answer. Liam, I already got yours. So I just want to know how many of you have answers. Looking good. I have a different question that I want to ask you now for a little bit of feedback. Green or blue, which one did you use? Which method did you use? That's kind of what I figured would happen. I mean, you want to get the answer, right? Now, JV, you're like me. You want to do it in steps. And this is one of the rare cases where I would want to do it in steps in science in general. Normally, I just want to do the whole formula. So I'm not going to show my work here. This is being recorded, so if you want to see my work, you can watch it again later. If you use the blue method, you're going to take 4 times pi squared, don't forget to square the pi, times 0.06 meters, which is r, divided by, you're actually given the period here, 0.1 squared, 4 pi squared times r over 0.1 squared. I'm getting 237. Did anybody else get 237? Okay. So 237 meters per second squared, which, so the object, this is the meaning behind a centripetal acceleration. The object is not speeding up or slowing down, but we can always compare that acceleration to the acceleration due to gravity by dividing by 9.81 and saying, wow, if you were on the edge of this, I know it's too small for you to be standing there, but you would be experiencing a force 24 times the force of gravity. It would be very hard to hang on. If you do it using the other formula, then you're going to take 2 times pi times the radius divided by the time. You're going to get a speed of 3.8 meters per second. Then you're going to square that and divide by the period, no, divide by the radius, but you still get the same answer. All right, let's move on and look at number 3. During a roller coaster ride, a car moves through a circular part of the track with a radius of 15 meters. People experience a centripetal acceleration of 25 meters per second squared, which, not needed for this question, but just a matter of curiosity, that's about 2.5 Gs. And tomorrow we'll talk in more detail about G forces. Most people can't stay conscious at about 4 Gs. So if you are sitting and you are experiencing 4 Gs towards your seat, the blood rushes to your feet and you pass out. Okay? And other effects happen that we'll talk about later. We want to determine the speed. Well, this is pretty easy because centripetal acceleration has a magnitude of v squared over r. So we can put 25 in for the centripetal acceleration. For r, we can put 15 meters. And we have to solve that equation for v. V squared will equal 25 times 15. Is 25 times 15 3,750? No. Oh, just 375. Got too many decimals. Okay. So this is 375. That means we have to take the square root of 375. So about 19 meters per second. That's the answer. Any questions with number 3? All right, number 4, this is the last question. Well, there's 5 as well, but it's related to 4. You've got a 1,600 kilogram car rounding a curve on a highway. Determine the acceleration and force. So for each of these, we're going to have a centripetal acceleration and a centripetal force. We are sure as shooting not going to be showing all of our work for this question, because we're going to have then 10 calculations in total here. What we're going to do is write down the formulas for how we would find these. And do the calculations. So how do we determine centripetal acceleration? Well, that's easy. It's v squared over r. How do we determine centripetal force? Well, it's the mass times the acceleration, because centripetal force is net force. The only problem is here, everybody, we have to use standard units. So you need to remember that meters per second equals kilometers per hour divided by 3.6. So let me show you how we can make our lives really easy here. So you're going to need your graphing calculator. And in your graphing calculator, there's a section where we enter data. We have talked about this before, but I want you to go to your lists, which is stat. You hit the stat key, and then you hit enter. The stat key is kitty corner from your apps key. And what I'm going to do is in list 1, I'm going to enter these 5 speeds. I'm going to enter 70 kilometers per hour, 80 kilometers per hour, 90, 100, 110. Now we're going to quit out of there and go to the home screen. Now, what is it we need to do? Somebody type into chat what it is we need to do to the speeds given in the question before we start using the formulas. What will dividing by 3.6 do? So mathematically we need to divide by 3.6. Why are we doing that, Liam? Yeah, we need to use meters per second. Change it to meters per second. So watch what I do here. List 1 is all of the kilometers per hour. Look at the second feature of every number on your keypad. The second feature of 1 is L1. The second feature of 2 is L2. So if I hit my second key, which is the yellow key, and then I hit the number 1, L1 pops up on the screen. And I want to take every item in L1 and divide by 3.6. Okay? Now, if I do that right now, it's going to give me a list on my home screen of the speeds after they're divided by 3.6. But if I go into my stat lists again, nothing's happened. So what I do is I take L1 and I divide by 3.6, and then I'm going to store it in L2. And the store key is the key immediately to the left of the 1. So I hit store, and now I'm going to select L2 and hit enter. Once you do that, go back and look at your lists by going stat edit. We've got a new list now. The new list are the speeds in meters per second. Okay, let's quit out of there. Now what I need to do is calculate the acceleration. But the acceleration is v squared over r, and v is L2. So we need to square list 2 and divide it by the radius of 50 meters. But we need to store that someplace, so we're going to see it. So I would do that calculation and store it as L3. So rather than doing the same calculation over and over and over again, just to remind you where we're at here, we have in our list L2 is the speed. Rather than squaring each of those and dividing each of them by 50, I'm going to do that here. I'm going to take L2 in my home screen, L2 squared, and I'm going to divide by 50 and store it as L3. And now if I were to go to L3, I would get all of my answers for the acceleration. So this is my acceleration for question A, for question B, for C, for D, and for E. I've got all of the answers. Okay, what if I want to know the centripetal force? Well, I know that to get centripetal force, I multiply the acceleration by the mass. Okay, but the acceleration is in L3. And the mass is, what do we got for a mass? 1600 kg, which means that if I quit out of here, and take 1600 multiplied by the acceleration, which is L3, I can store it in L4. I don't know how many lists you have. I think it might be 10. It might only be 6. But anyway, now if I go to my lists, I might have to scroll over to see L4, but these are my forces. That's the force in A, in B, in C, in D, and in E. That calculator with the list features makes multiple calculations very simple. So the acceleration in A is 7.56, then it's 9.88, then it's 12.5, 15.4. 18.67 is starting to get uncomfortable. We'll talk tomorrow about why this direction is what it is, but you guys have been in vehicles that turn corners sharply. I know you have. Everybody has. And when you have a vehicle turning sharply to the left, you feel pulled to the right. Many of you have been on rides. There's one ride, it's just a silly ride, there's nothing complicated about it, called the Polar Express. And you sit in this cart and it just goes around and around and around, faster and faster and faster. And you get sucked to the outside. You get pulled to the outside. With this acceleration, you would be being pulled to the outside with twice the acceleration due to gravity. And that leads to the next question. 18.7 is almost twice 9.81. Not quite. The next question is, how many G's are all of these experiencing? Well, I guess what we would have to do is take the acceleration, the number of G's, is the acceleration divided by 9.81. That's kind of what we're doing here. So I'm going to take the acceleration, and I might need to look in my calculator. You might as well. I believe the acceleration was in list 3. So I'm going to take list 3 and divide by 9.81 and store it. I mean, you can store it wherever you want, but I'm just going to continue by adding to my lists. I'm going to store it as L5. You can actually store it back as L3, but it would replace L3. Now when I look at my lists, these are the number of G's. In question A, you're experiencing 0.77 G's. In question B, you're experiencing 1 0.01 G, then 1.27 Gs, 1.57 Gs. You're starting to have a really difficult time here. Even at 0.77 Gs, it's like 77% of your weight is being pulled to the outside. That G is gravitational field strength, not grams, obviously. And this is 1.90 Gs. Any questions with examples 4 or 5? All right, so there are questions dealing with centripetal force and centripetal acceleration. Let me just run through them quickly to see what we're talking about here. There are 7 questions, I believe, in the handout, and there are a number of questions in the textbook. What I would say to you is you have to complete those 7 questions. That's your assignment. Class doesn't end for another 45 minutes, so if you finish those 7 in that 45 minutes, I expect you to continue and now work on the textbook questions. But once class ends, your assignment that you need to have done for tomorrow are the attached problems in the handout. Don't forget as well, your assignment number 2 is due tomorrow. Generally speaking today, too fast, too slow, or just right, please and thank you.